All right, guys, I'm going to keep this kind of quick. This is, for the first couple minutes, definitely about section 10.7, but I'm also going to get into a little bit of 10.8 and 10.9. So I'm going to kind of finish out the chapter with these notes. So you can stop taking notes after 10.7 because that's what your quiz is on. But I think it's worth an explanation as to some of the other stuff that's coming up. Kinetic molecular theory is a way to describe how gas particles move and why they move the way they do. So this is a model, so that gives you an idea that like it's one of those things that we guess this is how it is, but we guess this is how it is because it's based on data that we get. So it's like a lot of theories that we have where we obviously hope it's true. We don't know exactly for sure, but all the data seems to suggest that. So let's continue on here with this. Let me just get a marker that works. There we go. So this is a model that aids in our understanding of what happens to gas particles and environment conditions change. So what does that mean exactly? Well, here are some of the main points of the kinetic molecular theory for gases. So gases consist of large numbers of molecules that are in continuous random motion. So they're always moving around. They always have a lot of space in between the two, like in between the particles, and when they get close to each other, sometimes they hit, sometimes they don't, but for the most part, they just fly around and bounce off the walls and bounce off each other. The combined volume of all the molecules of the gas is negligible. That means the particle itself, like the little billiard ball or the little BB that's flying around, the volume of that little BB is insignificant or not important compared to the amount of space the molecules flying around take up. Okay, so like the container the gas is contained in is a lot larger, like a million times larger than the actual volume of what the particles would actually take up then, if you were to stop them from moving and let them settle at the bottom. So attractive and repulsive forces between gas molecules are also negligible, which negligible actually means like not worth measuring, basically, because it's such a small amount. So that means that even though you may have like gas particles of ions, where they're like plus particles flying around, they don't repel each other enough to make a difference for the path that they fly, where these gas particles are flying around, bouncing off the walls and bouncing off each other. So they're bouncing off each other just like when you start a game of pool and there's the loud crack and all the balls are kind of like flying around on the pool table. Like they're not attracted to each other and they're not repelled by each other, and that's what gas particles act like for the most part. So energy can be transferred between molecules during collisions, but the average kinetic energy of the molecules does not change with time. As long as the temperature stays the same, the gas particles do not lose their energy from colliding into each other or colliding into walls. In other words, the energy from a collision is conserved, which means that they bounce off each other very well, almost like two rubber balls bouncing off each other. So the impact is not deadened in any way. Like a car crash, the energy is not conserved. The energy is transferred and absorbed, but for gas particles, no energy is absorbed. Okay, let's keep going. So the average kinetic energy of a molecule is proportional to the absolute temperature. The absolute temperature, of course, means Kelvin. Okay, that's what it should be reported to, as in like 0 Kelvin means a molecule with no speed or no kinetic energy. Okay, good. So honestly, those are the main parts of Chapter 7. I would like you to read through an example problem, though, in Chapter 7 with the section 10.7. I keep saying Chapter 7. That's not what I mean. I mean section 10.7, Chapter 10, Section 10, Section 7. Jesus, Bensing. So this right here, a fusion, is the start of 10.8. So what is a fusion? Well, a fusion actually rides along with kinetic molecular theory because the kinetic molecular theory for gases explains how a fusion works. A fusion is a small pinhole where gases are allowed, like gas particles are allowed to escape into an evacuated area, which means that some gases will escape quickly and some gases will escape slowly, and it's all based on their molecular weight. So something like hydrogen H2 has 2 grams per mole, which would be the quickest gas to diffuse ever. We don't know what the heaviest gas is because it just kind of like keeps going up and up like the hottest temperature. You can always make it 1 degree hotter. But hydrogen is the lightest gas, which means it's the quickest gas. So let's keep going. So diffusion is the spread of one substance through a space or through a second substance. Like when I open a bottle of perfume in the back of the room, diffusion would be how long that perfume takes to filter out throughout, not filter out, but diffuse through the air molecules already in the room. So we're not sitting in a vacuum. That would be effusion if you're in an evacuated space. So diffusion is like the perfume molecules flying out from that perfume bottle and then bouncing off air molecules and working its way to me in the front of the room or you on the side of the room. So that would be diffusion. So most of the time we're actually talking about diffusion. And there actually is, you can actually measure diffusion, and that also is dependent on molecular mass. So hydrogen again would be one of those things that would diffuse the quickest. Okay, this is what I mean by this is going to be a short one, and I'm already at 10.9, the difference between real gases and ideal gases. In 10.4 we had the ideal gas law. So 10.4 was the ideal gas law, and we said a whole bunch of stuff like hey, ideal gases, they don't have any volume. Now, the gases, when they spread out, have volume in a container, but an ideal gas is like this molecule floating around that does not have volume. So if you decrease the temperature to 0 Kelvin, then you would have nothing left because there would be no volume of those gases, which is kind of a strange concept, but that's the one that works really well. So for an ideal gas, though, the reason why we have ideal gases when they actually don't exist is so that we can have a very nice and easy ideal gas law equation. And this equation works really, really, really well 99% of the time. So the only time it doesn't work well is when real gases deviate from ideal gases. And when would that be? Well, we're going to talk about that. So the real world, the behavior of gases only conforms to ideal gas equation, relatively high temperatures and low pressures. So that means that in common everyday circumstances, that would be considered relatively high temperatures because of 0 Kelvin. 0 Kelvin is so low that the temperatures that we exist in, is 270 to 290, 300 degrees higher than absolute zero. So that would be relatively high temperature. And by low pressure, we mean atmospheric pressure. Atmospheric pressure is relatively low. You can get a lot higher in pressure than atmospheric pressure. So just to give you an example, the 101.3 kilopascals is the atmospheric pressure, but when we talk about, that should be an equal, but compared to the 16,500 kPa that we use for to store like those tanks of gases in one of our 10A problem set. I forget, it was 48 or whatever it was, 56, 48 I think it was. It doesn't matter. Whatever the question was, maybe it was 40. Like this is the pressure that we have. When we get pressure that high, 16,500 kPa, then we may be moving closer to non-ideal behavior. Excuse me. So when do we have non-ideal behavior? When does a real gas act like a real gas and not an ideal gas? Well, that's easy. So when we have low temperatures, so if real world gases behave like ideal gases for relatively high temperatures and low pressures, then that means that anything that is high pressure or low temperature is going to behave like a real gas instead of an ideal gas. Well, what does it mean to behave like a real gas? Well, now notice that if we force gas molecules close enough like this, then their attractive forces may actually like overcome the motion of the particle. So it's like the billiards ball that slide by each other without hitting. One's going this way, the other's going this way, and they don't affect each other's path at all because they're not touching at all. Now, for a real gas, they may deflect each other's path because they are. So if it's going this way, it may deflect this way, and this one may deflect in a different way because of a repulsion force. Like if we have ions and they're both positive and they repel each other. So that may happen for a real gas, and that behavior only comes out when we have extremely low temperatures or extremely high pressures, because high pressures means we're forcing enough of the molecules close to each other, enough of them are around each other where the actual intermolecular attractions and repulsions actually outstrip, or like the forces are greater than the kinetic motion of the gases otherwise. So that's the difference between real gases and ideal gases. There actually is something called the van der Waals equation. The van der Waals equation is for a real gas behavior and should be used when there's a situation. This is what it looks like. Look at this mess. Okay, notice that we still have PV equals nRT, except the P term has to be adjusted because of the pressure issue. Okay, the V term has to be adjusted because of a volume issue with the interactions between the molecules. So you have to get these, all of these things that you see for the A and for the B, they all have to be accounted for now when we have the van der Waals equation. Turns out the difference between the ideal gas law equation and the van der Waals equation under normal circumstances are very, very, very close, which is why we use PV equals nRT and not this mess. Okay, that's it. That's what I'm going to talk about. If I want you guys to do an example problem, I will do a screencast separate for this. Okay.